Hello again, it's your friendly heavy physics teacher, and we are starting a new unit, okay? This is for my college physics class, Unit 10, Lesson 1, and we're going to be looking at the characteristics of simple harmonic motion in order to introduce us to the concepts of vibration, how vibration affects energy, and how vibration is what waves do to move energy from one place to another. Okay? So here we go. Simple harmonic motion. Yes, I'm using what I have at hand. Okay? So here I have a toy dragon suspended by a string above the table. Okay? And without me doing anything to it other than, trying to hold it in place, notice that this is what we would call its equilibrium position. But if I move it out here, I have moved it away from equilibrium. And the angle of the string here is creating a tension that is now at an angle to gravity, which is acting straight downward. If I let the dragon go, the dragon is going to move back and forth with some sort of periodic motion. Now, its interaction with the air and its interaction with its surroundings turn that into complex harmonic motion, okay? But the linear motion of it just going back and forth like so, that is the simple harmonic vibration that's occurring simply because we've got an interaction between the tension of the string and gravity trying to pull it back to this location, the equilibrium position. Now, I'm sure you can think of a whole bunch of different other kinds of simple harmonic motion interactions. All right. For instance, if I were to drop a bouncy ball onto a hard floor, you would expect it to bounce up. If I don't catch it, it's going to fall down and bounce up again, fall down and bounce up again. And slowly over time, we know it decays. But what if it were ideal? What if it were a perfectly elastic bouncy ball and there were no air friction, there were no loss to the air? If I drop it from a certain height, I would expect to be able to put my hand there and it come back and it would just touch my hand and go down and just touch my hand and go down and just touch and so on and so forth ad infinitum in a perfectly ideal situation. What if I had a spring that I suspended from this bar and I put a mass on the end of the spring and I pulled that down a little bit? We would expect that to vibrate up and down and up and down, okay? All of those forms of repeated motion, when the repeated motion occurs within a specific amount of time, is known as simple harmonic motion. All right, definition. Simple harmonic motion, or SHM, is any vibrational or repetitive motion that occurs in a specific repeated amount of time. Okay, so examples would be pendulums or vibration of masses on a spring or bouncing super ball. All right, for example. Okay, there are other forms of simple harmonic motion. Some would say that planetary motion is a form of simple harmonic motion because the planets repeatedly vibrate by going around their orbit of the sun. Okay? And so, viewed from outside the solar system, the planets go back and forth across the plane of the solar system over time. And so, in that way, we can think of more wild applications of this rather actually quite simple principle. Okay? So, when we have a vibrational situation, we have specific vocabulary that's associated with that vibration, with that harmonic motion that's taking place in a repeated, specific amount of time. Okay, so here's the basic vocabulary for the characteristics of simple harmonic motion. All right, period. Period means time. It means a specific amount of time for the full motion, the full repeated return to the original position to happen. So, period of time for a pendulum would be the time it takes to start over here, swing out, and back. That's the period of a pendulum. For a mass on a spring, if the spring were vibrating up and down, if you pull down on the mass and then it bounces up and then back down to that start, the time it takes to go from here up and back down to the start, that's period. Okay? The time to make one full vibration, period. We give it the capital letter T because it is a specific, fixed, repeated interval of time. The rate of vibration we call frequency. How quickly it goes up or down, how quickly it goes back and forth. We give that the symbol F, all right? And since it's a rate of vibration, it's how many cycles you make per time period. And since most time periods are calculated in seconds, a certain amount of seconds, then this would be in an amount of number of vibrations per second. Okay? So frequency, oscillations per second, vibrations per second, cycles per second. Now, a German scientist by the name of Heinrich Hertz did a great number of experiments verifying the electromagnetic waves equations and verifying them with physical empirical tests that demonstrated the wave characteristics of electromagnetic waves. And because of his contribution to our understanding of wave motion, specifically electromagnetic wave motion, we honor him by giving his name to frequency. So 1 hertz, H-E-R-T-Z, 1 hertz is equal to 1 vibration per second. All right? Amplitude. Amplitude is a distance measurement. Amplitude is how far physically out from the equilibrium position the object will vibrate each time. So when we pull the pendulum out, that's its amplitude. Okay? When we hang the mass from the spring and then pull that beyond that natural hanging position, that equilibrium position, when we pull it beyond that, that's our amplitude. Okay? For a bouncing ball, if I release it from a certain height, then it's going to return to that height. That's its amplitude. Amplitude is the maximum distance that it will vibrate from equilibrium, or it was the maximum distance at which that motion started that it goes back and forth from. Okay? So period, time to make one vibration. Frequency, number of vibrations per second. Amplitude, how far it vibrates beyond the equilibrium each time. It's not from here to there. It's from here to the equilibrium position, and then from the equilibrium position out. All right? So if you have a mass on a spring, and this is the equilibrium position, and then I pull it down, that's the amplitude. If I let it go, it doesn't stop here. It moves through there. It'll stop up here, whatever this amplitude is. All right? Notice my amplitude goes above and below the equilibrium, or to the left or to the right of the equilibrium, depending on what kind of vibrational mode you have. Okay? Now, what if we want to know where something is located within a particular cycle? What if we want to know how fast it's moving within a particular cycle? We also know that it's continuously accelerating throughout it, but it is not a constant acceleration. There is a time at equilibrium where the acceleration, the linear motion acceleration, is going to be 0. Equilibrium, position of balanced forces. Maximum amplitude, position of maximum acceleration. So how do we measure that? We use the following equations to do that. For the position at any time during the vibration, and this is the position from equilibrium. The position from equilibrium. Okay? So X, if we're talking about horizontal motion, this would be a Y if we were talking about vertical motion. So X equals the amplitude times the cosine of 2 pi over t. In other words, a full cycle divided by the time it takes to make a full cycle times the amount of time within that cycle. Okay? This small t over here is the time within the cycle. All right? The velocity at any time is equal to whatever maximum velocity it might have as it moves through the equilibrium position times the sine of the full cycle, 2 pi, over the time to make that full cycle, divided by the time within that particular cycle. Okay, so if you have a 2-second cycle, how fast is it going at 3/4 of a second? How fast is it going at 1.2 seconds? How fast is it going at 1.75 seconds? That is what we would be putting in here. This would be 2 seconds because that's the full period. Okay? The acceleration, how quickly this is changing from Vmax to another velocity within that cycle. How quickly that's changing depends. Notice the negative sign here? This means that the direction is always opposite to its displacement. So the direction of acceleration is always in the opposite direction to the displacement from equilibrium. So that's why the negative sign is there. So the acceleration is whatever maximum acceleration would have at its start times the cosine of 2 pi over t, capital T being the period, times the time within that cycle. Okay? So the maximum velocity you will have, if you know the amplitude, you can determine the maximum velocity as long as you know the frequency. Well, frequency is 1 over period. So if you measure the period of vibration, it takes 5 seconds to go back and forth once. Take 1 over that, and that's your frequency. So it's frequency if it's 5 seconds to make 1 cycle, then it's 0.2 cycles per second, all right, or 2/10 of a cycle. And so that's what we would put in here to figure out Vmax. Amax, you got a squared term there. Notice the squared term, okay? But notice that both of these depend on the frequency of vibration, or the period, because frequency is the inverse of period, and the amplitude, okay? And so that's what we're going to use to calculate any location, any speed, and the acceleration at that particular location during a cycle of vibration. Okay, that's how we go about doing it. All righty? Simple harmonic motion happens because you have a conservative force, gravity, the elastic force of a spring, the internal elasticity of a superball. You have a conservative force that is attempting to restore the object to its original position. The problem is it doesn't stop there. It goes to the other side. And then the conservative force is going to attempt to return it back. In the case of a bouncy ball, we've actually got two conservative forces acting. You let go of it, the equilibrium position for the bouncy ball is the ground. And so you let go of the ball, it goes down. Now it presses into the ground. The ball compresses. The equilibrium position is the original dimensions of the ball. So the elastic property of the ball is attempting to return it to that. But in so doing, it exerts a greater force on the ground, causing it to bounce back up. So now gravity is attempting to pull it back down to the equilibrium of the ground. Do you see how the combination of the two conservative forces are going to create that motion? And as long as there's no friction, as long as there is no non-conservative force acting on the system, that will continue forever. All righty? So we're going to apply this to springs. We're going to apply this to a pendulum. And that's coming up in our next couple of lessons. All right? Thank you very much. And hope to see you online soon so that we can discuss the implications of this. And I'll also go through a couple of problems with you that are associated with this. Okay? Thank you very much and see you soon.